Okay, so we're going live now. As we celebrate ISRO's historical achievement with the successful landing of the Chandrayaan III on the south pole of the moon, thus establishing India as the first ever country to do so, we are proud to be joined by a key member of the esteemed organization which made this world-defying dream into a reality.
We are honored to welcome Dr. Tirtha Pratim, Director of Space Science Program at ISRO, an integral member of all ISRO-related space exploration missions, specialization in the spaceborne instrumentation as well as launch vehicle technology.
I am Akash, and this is Sai Pranav, and we'll be your hosts for today.
Hello, sir. It's an honor to have you here with us today for the space hosted by Pragyan, the Techno Manager Fest of NIT. It brings with us a great joy to have a figure who played a vital role in a fabulous chapter in our history with us. Let us now move on with the presentation.
So thank you very much. So if I'm audible and if everything is set, shall I start the presentation?
Yeah, sure, sir.
Okay, so thank you very much for this opportunity. And let me tell you, I'm very happy that you have given me this opportunity to speak about moon and the scientific context of the moon. And like every Indian, we all are very proud. Internationally also, there has been a lot of enthusiasm, and I should tell many countries have, wanted India to win in this lunar journey, and all of them are happy in the prospect of very good science which is going to come. So before I start, I would like to tell a small clarification. It is not the case that we have landed at the lunar south pole. That is not correct. Where we have landed, it is basically 69.3 degrees south. Okay, so it is near the polar region, but it is better to say it is the higher lunar latitudes. So it is not at the polar region. So this is a small clarification. So what I will do is I will start my presentation. So before that, I would like to ask you that whether my presentation is visible to you in full screen.
Yeah, it's visible. Sir.
It is visible. Okay. Yeah. So I'm going to speak about the context of the exploration. So when I mean the context of the exploration, I mean the following. I mean that we have sent a mission to moon, and it is indeed a matter of glory in terms of technological achievements, in terms of national capability building. Fine. But significance of sending a mission to the moon. So that is the context. And then I shall speak about India's journey in the lunar exploration. And while I speak about India's journey about the lunar exploration, I shall speak about Chandrayaan I, Chandrayaan II, and then I shall delve into Chandrayaan III and what we can do in future. And I believe this lecture will be attended offline also by a number of young students, and to them there will be a lot of opportunity to work more on moon. So with this, let me begin. So we often come across some news that some space agency has sent some scientific mission to moon or Venus or Mars or some celestial body or the other. Now the question is how these missions are planned. Is it just like that the target celestial bodies are chosen? The answer is no. What actually happens is we start from a fundamental question, and when we say a fundamental question often sounds philosophical. Okay, it is very different from what we understand as so-called science. So the fundamental question could be as general like this: how did the solar system start and how it has evolved, where it is heading to. So these are all philosophical questions. You will not be able to figure out whether this is a scientific question or it is something poetic. That's why it is philosophy, and that's why it is fundamental. But this fundamental question has to be answered. If we have to answer this by gathering information, gathering evidences, the procedure is you have to disintegrate the fundamental question to a set of semi-fundamental questions which sound a bit more technical or scientific. And while you do this, that's why I've mentioned this second step, split this fundamental question to a set of specific questions. And in this step, set your target. So set your target means that particular specific question would tell you which will be the apt celestial body for you to do the investigation on that topic. For some of the scientific problems, it will be apt to study Moon. For some of the problems, it will be apt to study Mars. For some of the problems, it is apt to study Venus or some other, say, asteroids or comets. So they're all members of the solar system, and depending on the scientific question, you have to choose very prudently which body will give you the answer, possible answer to some semi-fundamental problem. And if you go on sending lots of missions and go on answering these kinds of semi-fundamental questions, you are inching towards answering that fundamental question. And then once you identify the target, suppose you identify that for some of the semi-fundamental problems, the best celestial body to study is the Moon. Then the next step is the third step. Identify the domains that need to be studied. What are the domains? You can study the surface of the Moon. You can study the subsurface or interior or the atmosphere of the Moon. So when we say atmosphere of the Moon, you may say Moon does not have any atmosphere. Statement is correct, but a more correct statement would be Moon has a very tenuous atmosphere, very thin atmosphere, which we called an exosphere. So on and so forth. So these are the domains, right? Now, once you are done with choosing the domains which you want to study, you have chosen your target. In this case, it is Moon, let us suppose. And then you have chosen that I want to study the surface of the Moon. Then the question is what exactly you want to study on the surface. And then once you define what exactly you want to study about the lunar surface or interior, whatever it is, you would have to set a set of parameters, identify a set of parameters. I want to study, say, the surface reflectivity or the surface roughness, absorption coefficients, some parameters. Then you have to specify the ranges. So now you are entered into the numbers. So far you have been telling about what you want to do. Okay. Now you are telling about the numbers. My parameter 1 should lie between this and this with some error bar. Parameter 2 should lie between this and that within some error bars. Like this, a list comes, right? And then after having defined this, you also define that what are the techniques you would like to adapt, whether you would like to use a spectrometer or whether you would like to have an imaging camera, whether you would like to have a seismometer. So the technique and the scientific instruments. So the techniques lead to scientific instruments, which we called payloads. So you choose. So it's a chain of thought process, very logical, you must say. And then once you are done with up to this, then you choose the exploration platform. So when I say exploration platform, it could be an orbiter is a platform, like Chandrayaan II orbiter, it is a platform. Then lander is a platform, or the rover is a platform, like this. Then also define an observation plan. And observation plan means when to observe, what exactly you should operate in terms of the instrument, which mode you should operate. These are all finer details, okay? And then also you have to think about the ground stations. I'm generating this amount of data, and for the download rate, for a given download rate, I will require this much amount of time, whether from the Indian ground station it is visible, or I have to do collaboration with some other ground station. So these are all finer details, but it starts from a fundamental problem, broken down, target chosen, specifications are arrived at, and then the instruments are chosen, and then the science plan is evolved. So this is how any mission comes up. And the Moon is coming to the context because Moon, when you are studying in a particular mission, not only you are studying the Moon, the knowledge which you are gathering by studying the Moon, in many circumstances, it is applicable to some other celestial bodies of the solar system. So whatever science you are going to derive, not necessarily speak only about the moon, but something else also. Okay, and let me explain this to you in the subsequent slides. So moon is known as a differentiated planetary body. This is the technical term. What it means is like this. See, when the planetary system was formed, everything was in the form of molten substances that you know. The heat was so much that it was a molten, and because of the surface tension and gravity interplay, so they assumed spherical shapes. And then what happened? There was a process of radiation, cooling. So the heat of the surface started getting radiated in the free space, and in the process, what happened? The surface got cooled, and when the surface got cooled, the outer part of the spherical shapes, this got solidified. But before that, something happened. When it was all liquid and spherical, there was a process in which the lighter substances, because of their buoyancy, they got lifted up. And the heavier substances, heavier elements, they started sinking. And it so happened there was a gravitational filtering of the substances according to its mass. So the outer part of the crust of any celestial body, that became rich in the lighter substances, low density substances, while in the lower part, interior, they became rich in the heavier substances. And this process is known as planetary differentiation. Moon is also not an exception. Moon is also a differentiated planetary body. And another speciality of Moon is an airless body. So as I mentioned, Moon does not have any substantial atmosphere, so is airless. And it is also a fact that since it is airless, the solar radiation of all the wavelengths reach the moon unhindered, which is not the case in case of Earth. Right? Because of the Earth's atmosphere, many of the wavelengths are absorbed, but that advantage is not there in moon. Everything comes. Then, unlike Earth, moon does not have a global magnetic field. Earth is having a global magnetic field, moon doesn't have. But what is present on moon is, a system called mini magnetospheres. So mini magnetospheres are small patches of magnetic field. So usually I explain it in this way. You cannot see magnetic field with your bare eyes, right? But suppose you are gifted some power to see magnetic field with your bare eyes, the magnetic fields on moon will appear like igloos. You know igloos? The Eskimos stay in the igloos, small patches or regions. So it will look like that. So small occurrences of local magnetic fields which open and close there. That's all. There is nothing which surrounds the whole moon. So global magnetic field is not there. And since the global magnetic field is not there, the ionized particles from the sun, which are called the solar winds, which are rich in hydrogen ion and helium ion and other ions, other heavier ions, plus the electrons, they reach the surface of the moon unhindered. In case of Earth, what happens? Because of the magnetic field, global magnetic field, there is a process of deflection of all the charged particles. That doesn't happen on moon. And another feature is moon has a surface boundary exosphere. The meaning of the statement is moon has an exosphere. I have told you the meaning of the statement exosphere is, if you consider 1 cubic centimeter of volume on Earth's surface, it is containing about 10 to the power 19 atoms in that cubic centimeter of volume. So these atoms and molecules are in constant collision with each other. And so there is a concept of mean free path that also, those who have studied physics. So the mean distance traveled by the particles or atoms or molecules between the successive collisions. That's a mean free path. But imagine you are creating a vacuum. Okay. So when you are creating a vacuum, then the number of atoms and molecules in that unit volume becoming less. So we call the number densities is becoming less. And when the number density is becoming less, the collisions are becoming very rare. And when the collisions are becoming rare, the mean free path, that is the mean distance between successive collisions, also becoming very large. Okay. And when these are becoming very large, This how much is a very large is not a scientific statement. It's a very qualitative statement. So here comes some other concept. I will not delve into those concepts. There is a concept of scale height. So when the mean free path of between the two atoms or molecules in any region becomes so large that they're greater than the local scale heights, we call exosphere. And in different planets, this exosphere starts at certain heights from the surface. But in moon, the exospheric condition starts right from the surface. So that's why moon is said to have a surface boundary exosphere. And what happens, I have shown you a picture. So this, I am spending some time on this slide because I want to explain something. The later slides I can move faster. So I have shown a cartoon where I've shown a picture of the sun. I have shown a picture of the moon, and I have shown that something is coming from sun. That something is solar radiation is coming. That is one. Solar wind is coming. So when I say solar wind, it comprises the ions, the positive ions, and also the electrons. And the third entity that comes from sun is the solar magnetic field, which we call the interplanetary magnetic field. An interplanetary magnetic field is associated with these charged particles. They follow the helical trajectory along the lines of the magnetic field. And just imagine what happens. They're coming from the sun, and moon is sitting in between, as an obstacle. So moon becomes a substrate to all this flux of the entities which keep on coming from the sun. And when that happens, they impinge on the sun, they settle on the sun, and a lot of processes happen. So without going to much of details, I may mention about some of the processes which will be very important in the subsequent discussion. So what happens? One of the effects is, that when solar radiation comes, and the high frequency of solar radiation, the ultraviolet or extreme ultraviolet solar radiation, these photons have sufficient energy to knock out the valence outermost electrons from some of the atoms which are residing on the moon surface. So what happens when these electrons come out? So the surface, neutrals become positive ions, and these electrons are called photoelectrons because this is a photoelectric effect. And these electrons form a sheet around the day side of the moon. Thin cloud of electrons, they are formed because of the photoelectric effect. But some of the electrons are also contributed due to the solar wind, because solar wind carries electrons also. They also come, right? So near surface of the moon, a few meters, tens of meters of the moon surface, if you see, lot of electrical phenomena happens. First of all, the surface of the moon, which is in the day side, that becomes electrically positively charged. Night side becomes negatively charged, and there is a thin layer of plasma near the moon surface that is also there. And a lot of other things also happen, like when one side of the moon is day, one side of the moon is night, and in between the dawn dusk region, it is called the terminator. In the terminator, what will happen? Just imagine, in the day side it is becoming positive potential, night side it is having negative potential. What will happen? There will be a potential difference, right, between day and night, and something like a dynamo will happen. So there will be a transport of, the transport of charged particles also will happen, because charged particle always follow some electric field. So a lot of things happen. Very interesting thing happens when we look at moon from a distance. We don't know all these things are happening, but ask a planetary scientist, he or she would tell that all these things happen in moon. A lot of other things also happen when the heat, solar and moon
Wait one second, I'll say Tirtha first.
Yeah, so is it okay?
Yes, sir, you're audible, sir. You can continue from where you left off.
Yeah, we can do, but in the YouTube, I think the previous link is getting streamed.
Uh,
Yeah, I think in the YouTube, you still have the old link. Yeah, so is it okay?
yes, sir, you're audible, sir. You can continue from where you left off.
Yeah, we can do, but in the YouTube, I think the previous link is. Okay, so shall we start? Shall we resume the session?
Yes, sir, we can resume the session, and YouTube will have the continuation of till where you covered.
Okay, fine. So let me share the screen once again. So can anybody tell me that which slide you are able to see right now?
Slide 2.
Which one?
The second slide.
Okay, fine. So I have been explaining the different phenomena that happen in moon, and so I hope I could give a very brief overview of what will happen in the moon. So instead of delving here more, let me continue for the next course of the journey. So now it is important to have an understanding of the formation of the moon, since I have mentioned that moon is a differentiated planetary body, and some echo is coming. Okay, so since I have described the basic process that heavier substances started sinking and the lighter substances, they, because of the buoyancy, they were lifted upwards, and when it solidified, there was a process of differentiation with respect to the mass of substances, density of the substances, and that's how it happened. The same thing I have shown here in this slide, wherein I am showing that after the solar system was formed, it took around 100 million years for the formation of the moon. And the presently accepted theory is that the moon was formed because of an impact with, because of the impact between the proto-Earth, young Earth, and the Mars-sized object. And it so happened that the portion which got scooped out of the Earth, as well as the material of the impactor itself, they merged, and thus moon was formed. This all happened in around 4.5 billion billion years ago. So GY is the giga year, which is similar to the billion year. So 10 to the power 9 years. So then immediately, as I have mentioned, magma ocean was formed. It was all molten lava in the form of a sphere. It was an interplay between the gravity and the surface tension, and then it started solidifying. Okay, and then the radiation was, it was escaping to the deep space, and the crust becoming harder, and now we have the present moon. But when I have described this, I must tell you that I have skipped a lot of steps. Okay, as for example, I have not told you that about 3.5 to 3.8 billion years from now, backwards in time, there have been a process. A process is like late heavy bombardment. So late heavy bombardment was a process wherein lot of leftovers of the solar system formation, all these small meteorites, or why should I say small, different sizes, small to big, they bombarded on the moon's surface, and that's how the different basins were formed on the moon's surface. And just imagine you have a cake, and in the cake the inside is molten, and you pinch the cake, what will happen? From inside the liquid part will ooze out, right? Same thing happened in the case of moon also. So that's how, when impact happened, the inner material came out and it was still liquid, and then it got settled because of the gravity. Same thing happens when you make cakes at home, right? So this process continued, and later on the solar system also got stabilized. This much bombardment subsided, became rare, and then we see the present moon. So that's how the moon's bulk has evolved. The moon's bulk means the solid part of the moon, the way the physical part of the moon we see, that got evolved over 4.5 billion years. But that was not all. When I speak about the evolution of the moon, the atmosphere of the moon also evolved. Today, when I say the atmosphere of the moon is negligible, it does not have any atmosphere practically, right? Why do we say so? We say so because if you see this picture, in the x-axis I have plotted time, giga or billion years ago, and in the y-axis, vertical axis, I have plotted atmospheric pressure on the moon. And here I have shown a blue colored horizontal line. The horizontal line is at 1 bar pressure, which is representative of the pressure, atmospheric pressure on Earth today. Now see what is the atmospheric pressure on the moon today. It is in the order of 10 to the power minus 14 or 10 to the power minus 13 to minus 15 bar. Night side, it is as low as 10 to the power minus 15 bar. And this is the kind of difference which we are speaking about between Earth and Moon. But if you follow this picture, there was a time initially, about 4 billion years or much before that, Moon's atmosphere was thicker than the Earth's atmosphere today. So we call it Epoch 1. And this atmospheric pressure was few orders of magnitude more than the atmospheric pressure that prevails on Earth today. And then it came down, it subsided, and then in between you're seeing a lot of spikes, right? So these spikes are nothing but, when these bombardments were happening, there was sporadic increase in the pressure, atmospheric pressure of the moon. So there was all of a sudden rise in the pressure, but that did not subside because of lot of phenomena, thermal phenomena, because of the solar wind. Many of them, the particles which momentarily got formed in the atmosphere, they got again vanished. So this process is continued. That's why you are seeing those spikes coming in between. But overall, if you see the tendency, the pressure of the atmosphere on the moon's surface got dwindled. Now it is almost no atmosphere. So what I must say to sum up here, not only the bulk of the moon evolved, but the atmosphere of the moon also evolved over the last 4.5 billion years. It was very thick, now it is very thin. Not only that, there is another twist in the story. The twist is that moon's orbit also has evolved. So without going to that details, I will tell you, moon sometimes decided to be very close to the Earth, sometimes it decided to be away from the Earth, again it decided to come back to near Earth. So this was all happening because of the gravitational interplay between the moon, the Earth, also the sun. Okay, basically it was a three-body problem, and it so happened in the process of stabilization, I should say, as in a poetic language, moon was not able to make its mind where to get settled. So that's why sometimes it was coming closer, sometimes it was going away from the Earth, like this. So in this slide, I have shown you two pictures. In the left-hand side, I have shown you the moon as seen in the night sky only 1,000 years after its formation. 1,000 years after the formation, that is still 4.5 billion years ago. At that time, you will appreciate there was no life form on Earth to have witnessed this moon. And the moon also would have looked, almost 12 times bigger than whatever it is seen right now in night sky. And it also resembled a fireball because it was all molten, radiation was coming out, okay? And it was all a molten fire, very close to the Earth, 12 times bigger than whatever you see today. And in the right-hand side, you see, tonight, if you have to see the moon, how small it is. And in between, a lot of things happened, as I have told you. So if I have to tell you, to summarize, how did moon evolve? Moon evolved not only in terms of its bulk, moon also evolved in terms of its atmospheric pressure. Moon also evolved in terms of its orbit. So, and now you see, when it was evolving in terms of its orbit and in terms of its process of solidification, another phenomenon happened. What happened was called tidal locking. So what is tidal locking? In classical mechanics, there is a phenomenon that is, if the tidal bulges of any body are misaligned with the major axis, the tidal forces exert a net torque on what the body twists the whatever causes the body to twist in the forward direction of realignment. So let me not delve into this complicated statement. Let me tell you that there was a process of synchronization between the two rotations, okay? Moon's rotation around its own axis and the rotation of the moon around the Earth itself. And it so happened, this synchronization happened in such a way because of the process of transfer of angular momentum that we have ended up seeing only one side of the moon always. And that side is known as the near side of the moon, and the side of the moon which we do not see from the Earth, the other side of the moon, is known as the far side of the moon. And you will appreciate, since the near side of the moon always faces the Earth, lot of electromagnetic interference, whatever we generate on Earth, they reach the moon. And if you happen to be on the far side of the moon, you are not going to see any RF or radio frequency interference which are coming out of the Earth. So you may think of different possibilities. And that's why moon offers itself as a natural laboratory to do two kinds of things. One is science of the moon, wherein you can study moon for studying the moon itself or to study the solar system. That is, you are studying the surface, subsurface, elemental composition, mineralogy, so on and so forth. And another option which you are getting is the science from the moon. That is, you are not studying the moon, but you are using moon as a platform to do a lot of studies like radio astronomy from the far side of the moon, gravitational wave astronomy, Earth observation, mere astronomical observation, and many more. Okay, so there are two arms of moon. And there is also another aspect. So far we have brought back some lunar samples thanks to the Apollo missions, Lunar missions, and Chinese Chandrayaan missions, and also the lunar meteorites which have managed to reach the Earth. So a total of a few hundreds of kilograms are available, which are amenable to scientific analysis. So that's how we are in a position to study about moon. Okay. So now, in this context, let me tell you that when you are designing a mission to study the moon, I have mentioned that in the whole process, there is a step wherein you have to define the observational techniques. So when it's observational techniques to study the moon, and let me tell you, these techniques are valid for studying any other solar system body. You can apply similar techniques to study Venus or Mars or any other system. So one technique is remote sensing, another technique is in situ observations. So wherein in the remote sensing, you study the object of your interest from a remote distance by virtue of the information which is coming to your instrument in terms of radiation or in terms of particles or in terms of some fields. Okay, so this is remote sensing. And remote sensing are also two types, active remote sensing and passive remote sensing. In active remote sensing, you shine the surface of your object of interest and the reflected or scattered part of the radiation you are studying. Just like you are carrying a torch and you are illuminating an object, and from the reflected light, you are making sense of what you are seeing. That is an active remote sensing process. Passive remote sensing, on the other hand, you are not illuminating it actively, whatever is coming out of the object on its own, you're analyzing that, and that is the passive remote sensing. You can compare it with a remote thermometer which you might have used during the coronavirus time, which was used to sense the body temperature without bringing it to the contact of the body. And then there are in situ observations wherein you're having instruments which are in touch with the object you want to measure. Just like, say, you are having seismometer. It has to be in touch with the body to understand the seismic environment. Or you can, as an analogy, you can see the conventional clinical thermometers, which we used to keep under the tongue to measure the body temperature. That is in contact with the body, in situ, at site. So these are the observation techniques, and there are many such techniques. Okay, and so with this context set, let me tell you India's lunar exploration program. And as you are aware, we started all this program with Chandrayaan I, which flew in year 2008. And Chandrayaan I was an elegant example of international cooperation, wherein we had 1, 2, 3, 4, 5 instruments, scientific instruments from India, and we had some European Indian instruments, which mean collaboration between Europe and India yielded 2 scientific instruments called KIX and SARA, and there have been instruments from United States, MCube, Moon Mineralogy Mapper, and Mini Synthetic Aperture Radar, MINISAR, and there has been European instruments called SAR2 and Radam. So these instruments made Chandrayaan I, and the theme was chemical, mineralogical, and geologic mapping of the moon. And this is a broad theme. If you can study this, you can know not only about the moon, you can translate this knowledge to other planetary bodies also within some limitations. Okay, and then we have understood a few science about the moon. And let me tell you, in the subsequent slide, I will give you a glimpse of how Chandrayaan I has revolutionized the understanding about the moon. So we have learned a lot about the moon, and this learning, what we have achieved from Chandrayaan I, have given rise to the mission Chandrayaan II. And there have been a lot of improvements in the instruments and the observation techniques, ranges, parameters, which prompted to redefine the set of instruments which flew in Chandrayaan II. And Chandrayaan II, it was initially envisaged to have an orbiter, a lander, and the rover, but the landing was not successful. It was not possible to do a soft landing. So we ended up in a hard landing. So that part of the mission was not a success. But the orbiter of the Chandrayaan II is still working, and with a suite of 8 instruments, which I have listed here, they are yielding fantastic science. And I shall tell a bit later in the course of the study what all science have come so far from Chandrayaan II also. And now with the observation from Chandrayaan I and Chandrayaan II, when we have understood globally what is happening on moon in terms of its chemistry, mineralogy, and geologic mapping, then we have understood that it is imperative to fulfill the dream which we have seen during Chandrayaan II, but we couldn't fulfill. That is to have a soft landing on the moon and to study the ground reality in terms of some in situ observations. And hence Chandrayaan II has given rise to Chandrayaan III with a suite of instruments. And the scientific objective in general was ground truth of the surface and near surface properties at the landing site. And you must be observing, when I have listed the instruments in Chandrayaan III, I have used 3 colors. The first set, which is shown in yellow color, these instruments are for measuring seismicity. Second instrument is used for measuring the near surface plasma environment. And the third one is for, it's a probe for measuring the thermophysical properties of the moon surface up to the first 10 centimeters. These were a part of the lander. And the second set of instruments, which is shown using orange color, APXS, alpha particle X-ray spectrometer, and the laser induced breakdown spectroscope, LIBS. These 2 instruments are the part of the rover. And in addition to the lander and the rover, we also have a propulsion module which was responsible to carry the lander rover composite to the moon's orbit. And this propulsion module, which is still, in the moon's orbit, it carried one instrument called SHAPE, which is spectropolarimetry study of the Earth. So it is observing Earth from the moon surface, and it is studying the spectrum in the infrared region. Also, it is studying the polarization of the radiation which is coming. Why it is doing so? Because when you go to focus on our solar system, which is outside our solar system, we call it exosolar system. There may be some host star, and there may be some other planets in that other solar system, wherein there will be some planets which we call exoplanets, and some of the exoplanets may be Earth-like. They could have the potential to harbor life. And then there are signatures of water, there are signatures of landmass, cloud formation, which come not only in terms of spectroscopy, but also in terms of polarization of light. And Earth is studied as a case study, so that what are the signatures which are coming from Earth. If we capture, we are getting prepared to use this knowledge when we study an exoplanet. That is a planet which is in some other solar system. So with this set of instruments, Chandrayaan III got ornated. So if you have to remember that in 2008, we had one achievement, the Moon Impact Probe, which was a part of the Chandrayaan I orbiter. It was made to impact on the lunar south pole, which was the first ever successful observation on the daytime lunar exosphere. There have been a lot of scientific papers which have come out of the Moon Impact Probe, and this Moon Impact Probe contained one instrument called CHASE, Chandra's Altitudinal Composition Explorer. This instrument was a mass spectrometer which detected for the first time directly the presence of lunar water vapor in the sunlit surface of the moon. Also, it has studied different noble gases and hydrogen molecule in the sunlit side of the moon. And that was a big success. And that was a mission which impacted. It was not a soft landing. It was intentionally a hard landing. And that time we were not equipped with the soft landing technology. But it has yielded a lot of scientific information about the moon's exosphere, dayside exosphere. That is a different story. And in this picture, I'm showing here wherever we have landed during the Moon Impact Probe mission Chandrayaan I, and where we have landed during Chandrayaan III. So these two places are marked here for your reference. So Chandrayaan I has changed the perspective about the moon. Let me tell you, before Chandrayaan I, we used to think moon is as dry as a bone. Moon is bone dry. But Chandrayaan I has discovered water molecules on the moon surface. Indications of the water molecule, I should say, not directly, because the technique which was used, it was not able to confirm that is H2O. It was telling it is hydroxyl, OH. And we understood that it could be from H2O. And then we got prompted that we should extend the range of the wavelength so that we can go for an unambiguous detection of hydrogen, H2O, sorry, unambiguous detection of water as water. We don't have to tell from hydroxyl detection that it could be water. So that was a signature which revolutionized actually that moon is hydrated. Okay, and then there was another belief that moon is geologically dead billions of years ago. But there have been evidences of recent volcanism in moon. When we say recent, geologically it is a few hundreds of million years. That is geologically recent. It is not 1 or 2 years, which showed that moon is still dynamic and volcanically active. And then another belief was the solar wind interaction with the moon surface. People used to believe that entirely the solar wind is to be absorbed by the moon surface, which was proven to be wrong during Chandrayaan I. It was proven that about 20% of the solar wind protons are reflected back to the space as energetic neutral hydrogen atoms. So the interactions also, the way the interaction happens between the solar wind and the surface, that concept also got changed. And there was also a concept that, lunar wake region, wherein lunar wake means the opposite side of the sun, wherein there is no sun's influence, is devoid of solar influence. which also was proven to be wrong because there have been detection of different populations of ions in the lunar wake region. And also there has been observations about the lava tubes, just like tunnels. If you have traveled in the Konkan railways, the Konkan railways offer a spectacular view of different tunnels. The trains enter the tunnels and gives you an opportunity to experience that kind of travel. Similar thing happens in the moon's surface also. There are tunnels which we call lava tubes, and those are considered as possible habitable zones in the on the moon's surface. So astronauts can go and stay there. So these things, these revelations, I should say, motivated Chandrayaan II. And that's how Chandrayaan II came into being. So what actually happened was this different set of instruments which were flown in Chandrayaan I, they were analyzed, the scientific outcome from each of the instruments were analyzed, and then we understood we need to have a different set of instruments with some improvements. Okay, in this slide, I am not going to read each and every row here. That is not necessary. This tells you about what kind of improvements happen in terms of the instruments, and then how the science got enhanced in Chandrayaan II. And one thing I must mention here, even if I don't mention the each and everything, Chandrayaan II carries the highest resolution camera present along any orbiter around the moon. India's Chandrayaan II carries a camera which is known as Orbital High Resolution Camera, OHRC, which offers you a resolution of 25 centimeter, which is smaller than 1 feet. So if you see things in perspective, if you see a meter scale, not meter scale, I'm sorry, a foot scale. Okay, so you will be able to differentiate between two objects which are 1 feet apart on the moon surface, seeing it from a distance of 100 kilometers. Just imagine you are looking at moon from a distance of 100 kilometers and you are able to resolve between 2 points which are about 25 centimeters away from each other. So that kind of resolution we are speaking about. And this is important because you are given access to detection of small craters on the moon's surface, which is important when you are trying to understand the crater size distribution on the moon's surface, which in turn tells you a lot of things about chronology of the moon's surface. So instead of delving into that subject, let me tell you the distribution, the frequency distribution of the craters on the moon's surface has got a lot to tell you about the chronology of the surface in that region. And if you have to make a complete picture, it is imperative to know the small craters also. So this instrument offers you that. At the same time, this instrument not only offers you to see or look at the small size craters on the moon surface, but it also provides you an opportunity to see the small boulders, and which is also important from the point of view of missions, space missions, especially the lander missions or the rover missions, wherein you are trying to identify a safe landing site. So in order to identify a safe landing site, you will be also interested to see what are the features available on the surface. So OHRC images of high demand for the global missions of this kind. So let me proceed and not spend much of a time here. A lot of excitement are there to share with you. Let me tell you that the scientific accomplishments of Chandrayaan II encompass the domain of lunar hydration, that is the water ice on the moon surface. Also, a lot of results on the moon's surface in terms of its geology, in terms of its lot of topographical information, its elemental composition, information about lunar neutral atmosphere, not atmosphere, I should say exosphere, also the ionosphere, and also this same Chandrayaan II has been used to study the sun. There was an instrument called XSM, X-ray solar monitor, which was studying this X-ray which is coming from the sun. So it has discovered a lot of microflares from the moon on the surface of the sun, and these microflares are very important, which got detected in the whole process. And in this, from the microflares, you are able to understand what happens in the background of the sun, and to some extent you can answer, get the clues about the coronal heating problem of the sun. And why all of a sudden we were studying sun? Because we carried another instrument called CLASS, which was looking at the moon, which was studying the X-ray which is coming from the surface of the moon. How these two are connected? These two are connected because the solar radiation, the solar X-ray, which is emitted by the sun, some of which was intercepted by the surface of the moon. And because of these impinging X-ray, some of the atoms of the moon's surface elements, they got excited from the ground state to the excited state, and they undergo a process of relaxation. In this process, they generate X-rays. So these X-rays are coming from the moon. So there is a cause, there is an effect. So CLASS was studying the effect, and the XSM was studying the cause. And from CLASS observations, the kind of X-ray which were seen, the spectrum of the X-rays used to tell you about the kind of elements which are present on the moon surface. So this technique is called X-ray fluorescence technique, XRF technique, which is used on ground also, especially in non-destructive testing. This is a very common technique which is used, and this we have used in Chandrayaan II in a planetary scale. Okay, so let me move forward because I should not take much of a time. So this Chandrayaan II and Chandrayaan I have given a lot of insight about the instruments which we should choose for Chandrayaan III. And this slide tells you about the different connections between the instruments which we have flown in Chandrayaan II and we have flown in Chandrayaan III. And let me also tell you, there has been a lot of opportunity for coordinated observation, coordinated science from Chandrayaan II, which was seeing the moon globally, and Chandrayaan III, which was a kind of spot measurement on the ground. So there was a good correlation, and there is opportunity for doing a lot of correlated study. And this slide tells you about the mapping which we have envisaged. So coming to the Chandrayaan III mission, scientific scope, I have told you about the different scientific instruments on the lander, on the rover, and the propulsion module. And this slide shows you only the pictures. I've already explained to you those things. I may not delve. So why we have gone to the near the southern polar region? Because of a few scientific reasons. One is the higher latitudes are relatively unexplored. You see the different missions sent by several countries. They were mostly in the mid latitudes or lower latitudes. Higher latitudes are relatively unexplored, and higher latitudes offer you different unique conditions like sun shines at a grazing angle. That is a condition where, which is experienced at the higher latitudes, and which has got some implications like lesser deposition of energy, solar wind ions and electrons, and also topographically, these high latitudes in the polar regions offer you lots of opportunities, geological opportunities to study. And technologically also, there were certain conditions when we have chosen the landing site. There were conditions on the global slope. There were conditions on the sizes of boulders and craters. There were conditions based on the shadow analysis, because wherever you land, it should not be a region which is cast by a big shadow. If you are engulfed by shadow of a boulder, what will happen? Your solar panels will not be able to develop power, generate power. So that was the condition. And also a condition of communication with the Earth. So these conditions, along with the scientific requirements, prompted us to choose this landing site. And 14th July, we had a spectacular launch from the second launch pad of the Satish Dhawan Space Center, Sriharikota. And then this picture, the left-hand side picture, is a picture which has been shot by the lander imager camera. There have been a lot of cameras in the lander, so I'm not going to that details. It was not a single camera, multiple of them. And this is a picture which was shot by the lander imager camera, and we are seeing the Earth, the cloud, and the ocean body. In the right hand side, I am showing you the mission description. So what I wanted to tell you, we didn't go to moon in one shot. We went to the moon by a process of extending the orbits one after the other around the Earth. We call it a process of Hoffman transfer. And Then there was a slingshot wherein we have had a kick which helped us to go up to a velocity which is greater than the escape velocity of the Earth. And then there was a coasting phase of about 4 days. So around 1st of August, we have been out of the elliptical orbit. We went to a hyperbolic orbit, and then it took 4 days. So around 5th of August, we were there somewhere near the moon, and we got captured by the moon's gravity in a higher orbit. Then we started lowering the orbit, and we were waiting for an opportune moment. And the opportune moment was the moment wherein there would be dawn or sunrise at the designated landing site, because we wanted to land at the landing site when there is the sunrise moment, and there would be some positive temperature on the moon surface, because your instruments have to survive and you should have enough time to study. And you have to remember, it is approximately one fortnight or 14 days, Earth days is equivalent to one moon day. And wherever we are landing, high latitudes, you are not getting the advantage of 14 days. You will be getting around 12 days. Okay, that you can draw the analogy from the Earth, what happens in high latitudes on Earth. And also, you have to remember, when you are landing at such a high latitude and you are seeing the transition at different local times, you are not seeing the transition of the sun overhead. Okay, you are seeing the transition of the sun near the horizon. Okay, because you are at the high latitude. So the temperature is less and illumination is grazing. So these conditions were prevailing. Now here in the next 5 to 6 minutes, before I conclude, I will take you through a journey how we went to the moon. So what you are seeing is some video which was shot on 20th of August. You are seeing through the eyes of the lander, and Chandrayaan III module is around the moon, and it was still orbiting around the moon. The descent of the lander module did not start at that juncture. It would take 3 more days to start. It was on 23rd of August when we started that process of descent. And there was a time when 23rd of August when we started the process of descent. And now for seeing the process of descent, the Chandrayaan III lander module started coming down, and how do you understand that you're coming down? Go on watching this video, you are going to see the average size of the craters started increasing. Not necessarily you're seeing big craters. This is happening
Sir, your voice is breaking.
closer to the moon. As you are coming closer to the moon, these craters has
Sir, excuse me.
bigger and still bigger, and you see the smaller size crater which you are not able to see otherwise when you are at a higher altitude. So in this process, you are coming down, and I must tell you, if you keep on watching meticulously, there will be a point of time when you are going to see that the motion, the relative motion of the craters with respect to the lander almost would come to a halt. That you'd be able to see almost there is no motion of the craters. That time, the lander was hovering. Hovering was maintaining its altitude and attitude. It was not coming down, it was hovering a few hundred meters above the surface. And it was analyzing whether it was supposed to land at that location, whether it is safe to land. So it was taking the picture, output processors was studying whether it is safe to land, and it was taking a decision whether to land. The process was going on, and few seconds or minutes you are going to see that moment wherein the lander seemed to hover, and all of a sudden you are going to see that there is no motion in the craters. Craters are standing still, and the lander is also maintaining its position and looking around and it's taking pictures. That moment has come. Then just was hovering, and that's why the craters are looking stationary. And then it decided, after taking pictures, that let's retarget and it went a few hundred meters and then landed. And then after landing, the ramp through which the rover would come down, that got deployed. And the solar panel of the rover got deployed, and the rover itself started putting on the ramp, and what happened? See, the rover started moving, and it printed the impression of its track on the moon surface. And next video is saying we just shot 25th of August. We're seeing very clearly the the tracks of rover on the moon surface, and we're seeing a process of rotation of the rover because we were trying to ensure a condition wherein the solar panel would face the sun to maximize the power generation. And we see some kind of movement of the rover. This is a fast bit, but not that fast. Reality. At least it was 4 to 5 times less small, less agile. Now, this is the track of the rover on the moon surface. And I must mention here that the location where the Chandrayaan III landed, the 69.3 degree and 32.3 degree. This point was named as Shiv Shakti Point by Honorable Prime Minister. And Honorable Prime Minister also has named the location where the Chandrayaan II crash landed. That location was named as Tiranga. And 23rd of August was declared as National Space Day. So all of you can celebrate the National Space Day. And currently what I am showing you is a simulation, or the track of the rover on the moon surface, and about 101 meter of distance has been covered by the rover so far. So let me tell you a few fast cut observations from Chandrayaan III. So these instruments have been healthy. We have been taking measurements, and these 12 days were very hectic for us. We were there in the control center, analyzing the data. While this data analysis is still going on, there has been some fast cut observations. First ever detection of sulfur on the moon's regolith, along with some trace constituents like carbon, nitrogen, phosphorus, titanium, manganese, chromium, nickel, and the process of quantification is in progress. And the first ever temperature profiling has happened on the moon's regolith for the first 10 centimeter depth. And the fast cut results show that lunar surface is very poor thermal conductor, and quantification is happening, which has got a lot of technological implications also. And there have been a few events of ground vibrations of the moon surface which are recorded by the seismometers. We have recorded vibrations because of the rover movement, because of the drilling of the Chaste probe on the moon surface. But apart from this, certain natural events also. Why this has happened? This could have happened because of the impact of the micrometeorites on the moon surface. That we are analyzing, and hopefully within a few months, we will be able to tell you a bit more about the science which have gone into it. And there also have been first ever characterization of the near surface lunar plasma at the higher latitudes, which indicate that only a few tens or thousands, not thousands, I should correct myself, few hundreds of electrons only are there per cc, and which is also dependent on the local time. Okay, these results are the fast cut observations which will come out, and all these results were put in the public domain in ISRO's website and ISRO's social media platform, wherein this is not the entirety of the science. We must tell you that the scientific analysis and serious science, what we say, will take some more time to come out, and which will be published. And let me conclude by telling about the future of lunar exploration. Having achieved up to this, the next logical step is to explore the polar regions of the moon, and with a suite of instruments which will be able to study the permanently shadowed regions of the moon surface, and especially to search the volatiles on the moon. And these volatiles contain a lot of information about the early solar system because these volatiles didn't get sufficient energy to get evaporated or sublimated and get lost in space because they have not got sunlight since the formation of the solar system. And then the next logical step would be to have the capability to drill the moon surface and collect the sample and analyze the sample in situ. Okay, and we should also have the capability to negotiate different difficult terrains, and also we should have technological capability to have rovers which should climb down and climb up steep crater walls because the walls of the crater contain lot of information in stratigraphy. And also, as a next logical step, we should be capable of sample return missions and also to have lunar bases, astronomical bases, not only astronomical bases, radio frequency observations, radio astronomy bases in the far side of the moon. And imagination doesn't stop here, there it is open. And that's why I call upon you to be energized, be a part of the India's lunar exploration. And let me end this lecture by telling you about the Indian Space Science Data Center. If you ever go to the website www.issdc.gov.in, you will be able to see the data portal of Indian space missions, wherein you are going to get access to the space mission data. And this will be a very good starting point for the students to get familiarized with the kind of data which are available, the techniques which are to be followed to analyze the data. The documentation files are also there. And what else you need? You need to have the contact details of the scientists if you have to talk to them to clarify certain aspects. Those details are also present in this website. Chandrayaan II data are available, Chandrayaan I are available. There are other missions data are also available, Indian science mission data. And Chandrayaan III data will be available after a certain period, which we call the lock-in period, which is present in any mission. Immediately the data is not made available to you. So stay tuned and visit this website, play with the data. I'm sure you're going to enjoy. And thank you very much for your attention and this opportunity. Thank you very much. I end here and I will be happy to take a few questions if there is any. And that's all from my side.
Thank you for your insightful session, sir. Now we have come to an end of our presentation.
Your voice is breaking. Your voice is breaking. It is not clear.
Session, sir.
If you wish, you can type the question in the chat box also, if you wish.
Yeah, thank you, sir, for showing your knowledge and wisdom with us. We are truly grateful for your time. And yeah, so we'll move on to the questions, sir.
Yeah.
Sir, we will be having another link for the Q&A session because this meet is running out of time, actually.
Okay, so we're going to have a fresh link for the question answer session?
Yeah, it will come in the chat box.
Fine, okay.
Can you send the link?
Okay, guys. You should never use mantle. I got a cleaning. He came and changed everything for the sake of Mac. That's I sent it. Everything I'm planning. Space with Pragyan. I sent it.
To mail.
I mailed it. Akash, you are there, the week, no? Huh?
The new it ended on its own.
No, another.
The new
I mean, the new media. I should mute the meter. Really, you are getting noise.
Yes.
Now we'll be moving on the quick Q&A session. So
Okay.
the first one is like you're into the thriller mystery in your writing works was most common. What drew you to the particular genre, and what about it resonates with you as an author?
The first part is the what led me to this particular job.
Genre.
So can you please type this in the chat box because the voice is not properly coming. So if you could quickly type this question in the chat box, it will be easy for me to understand. I'm sorry for this trouble. Oh, this question is different. Thriller, mystery in your writing works was most common. What drew you to this particular genre, and what about it resonates with you as an author? See, I like mystery. Okay, so since I like mystery, and I think the thrill, that mystery, that uncertainty, that guides everything. And if I tell you what guides me, it's basically you will appreciate everything in this universe has started because of uncertainty, right? Everything is because of the uncertainty principle. So there have been quantum fluctuations, and because of this fluctuations, all of a sudden the structure started forming. Okay, so that is how entire thing came into being. So there is uncertainty. Similarly, if you see uncertainty, if you don't know physics, don't care about physics also, a good story happens when there is uncertainty. If everything is certain, it doesn't become a story. So when there is uncertainty, this uncertainty can lead to many genres. Like it could lead to romantic stories also, it leads to patriotic stories also, it leads to the genre which you have mentioned. But now if you have to parameterize that kind of uncertainty which I like, which I love, or which I resonate with, it is the thriller genre. Okay, that's how the whole thing came. So fundamentally, it is the uncertainty of everything which turns me on.
Okay, so we'll move on to the next question.
Yeah.
I'm audible, right?
Yeah, it is. If you write, it is easy for me to
Okay.
understand.
Sure, sir. Sure. Yeah.
What were some of the pivotal events or experiences in your life that led to the choice of pursuing a career in space research? Okay, see, when I started my journey, I started as a launch vehicle person. I started with rocket science. So first 2 years of my career, I was working for PSLV and GSLV rockets. Then I switched over to the domain of planetary science. So to be frank, I was never expecting that I would work in rocket science. Okay, I came to rocket science by chance. Then from rocket science, I went to the domain of planetary science. But the very reason behind coming to ISRO was my urge to serve my nation, because I identified a few organizations. I believe that if I serve these organizations, I will be able to serve my country better. Okay, and Indian Space Research Organization has been in the top in my list of organizations which I targeted to join, because my background is also multidisciplinary. I have studied many types of subjects, and space is multidisciplinary. So I believed my kind of I should not say expertise, because none is an expert. Expert being an expert is a wrong notion. None of us are experts. These kinds of, what should I say, inclinations about multidisciplinary subjects would be very much appreciated in space domain. And I got chance, so I was fortunate to have been selected. So I joined, and that's how the journey began. So that's how it all started. The thing is, when you go on typing, there is a big silence. And this silence is actually
Oh no, sir. It's
uh,
yeah.
due to some reason, this audio which I am receiving from you, it is feeble. I have checked my speaker also, it is full volume, but somehow I am not getting the full volume from you. Space warfare has been happening since the Cold War era, At present, multiple countries are involved in it and making space a frontier. How are these things shaping ISRO for its space programs in future? So I would like to say that ISRO is a civilian organization, and ISRO as a space agency, it believes in the peaceful use of the outer space. So many of you must be aware about the UN Corpus, United Nations Committee for the Peaceful Use of the Outer Space. So that also, drives all the space agencies and the entities which are capable of space exploration. They are always encouraged to use space for peaceful use. But when you have some kind of threat from space, those threats are currently envisaged from some other sources. Like, suppose you're having a big asteroid which is coming and going to hit the Earth. Not necessarily a human being has to hit. Always there are small solar system bodies which are passing us. Some of them are burnt in the atmosphere. Some of them manage their way to reach the Earth's surface. And it could be catastrophic. So there should be a mechanism for identifying such objects which are threats to Earth, or to identify such debris which are around. This debris could be defunct satellites. This debris could be asteroids. Okay. In order to save the Earth itself from the collision, also to save the space assets, the satellites, which we are having at different altitudes, lower orbits is full of satellites, and many of them are not functional. So these are certain threats. And there is a domain where ISRO is gearing up. The domain is called Space Situational Awareness, SSA, and STM, Space Traffic Management. In these two domains, ISRO is getting geared up with the development of radars, in the development of techniques to detect different sizes of space debris and to understand which ones are going to pose a threat to the Earth and what are the corrective actions or the mitigation actions which could be taken. You must be aware, recently there has been a mission called DART mission. So in the DART mission, it was demonstrated how to, conjunct with an asteroid and deviate its path, its trajectory, which was otherwise destined to come and hit the Earth. You can fire some rocket so that it can deviate, it can make the asteroid deviate from its trajectory, and Earth in this process will be saved. This is called planetary defense. So that is another way to look into it. Another problem is, when I speak of planetary defense, I've spoken about space situational awareness. I've spoken about space traffic management. Another domain is your space weather. This is basically from sun. Solar influence is coming from sun, and lot of space assets are there. Okay, how far the Earth's magnetic field can save to a certain extent, but many space assets get, affected. You are very well aware that how a particular agency has lost a lot of satellites in one go. A few weeks or months back, this incident has happened. Okay, so what has happened because of this solar influence? There has been an expansion in the atmosphere, so the number density has increased, and which has caused the drag in the satellite. Okay, many satellites got damaged. These are a kind of situation which we have to be aware in terms of something coming, or in terms of debris or some defunct satellite, or suppose our manned mission is going, human mission, space mission is going, it should not get stuck by some micrometeorites or space debris. So these are the kind of planetary defense or awareness is ISRO is going to, ISRO is working. So if you visit the ISRO website and different public domain information, you are going to get a lot of information. It is not only about warfare. Okay, warfare is not our work. There are other better agencies, mandated agencies for that. We are looking for these kind of things which are somewhat beyond our control, which are more difficult in some other sense. So I think that answers this particular question. Thank you for the question.
Okay, sir, we'll move on to the next question.
Okay.
Sir, it's been typed in the chat box already.
What are your thoughts on the impact of the success of the Chandrayaan III mission on international space travel and potential future manned missions by ISRO? First of all, the impact is big. When I say impact is big, um, two ways or three ways. One impact is scientific impact, which is yet to come in terms of the publications. We are the first country to have landed, soft landed in the higher latitudes. So whatever we are going to see will be unique. So scientific impact. Second impact is the very low cost mission, very low cost, which is also talked worldwide, and successful soft landing. A lot of innovations have gone into it. And that's why it is very effective way it is managed. A lot of lessons have been learned, and that's why it is impactful. And we have been really congratulated by a lot of other space agencies for this kind of a feat. So there is a technological impact. When I say technological impact, you have to also understand that is also a national capability. One sort of capability we have demonstrated when we have sent the mission to Mars as Mars orbiter mission, wherein not only we have reached the Mars with the correct velocity and the correct location at the desired orbit, but also we have demonstrated the onboard autonomy, wherein we have mitigated the problem of 20 minutes of one-sided radio delay. Real time you cannot control. Also, you have to see the Mars orbiter mission went behind the Mars. There was an eclipse. So there was no communication, but it took care on its own, autonomy, onboard autonomy. Similar feat is Chandrayaan III, impact, soft landing. These have got a capability. It is a national capability. So if you name a very few countries who have got these capabilities, India has joined that rank, that impact. And there will be a lot of opportunities for spin-offs. When it's a spin-offs, technologies which come out of this feat, which will have a lot of business opportunities later. Okay, and when you have business opportunities, you can use some of the technologies for applications on Earth. The technology which you are using for rover today, can you not think of using such kind of technology for disaster management on Earth? Suppose an earthquake has happened. There has been a big fault line. Lot of misfortune has happened. Somebody is under the debris. You are not able to access. Can you not translate this technology which you have originally designed for space missions for the societal applications, wherein you will be able to send this kind of a rover with a sensor which can detect whether a person or any animal or any form of life is stranded beneath these rubbles, and which will enable the disaster management team to take the next course of action. So there are a lot of possibilities in societal field also. There is a term which you might also know, translational technology. So translation technology translates from the space domain to other domains wherein it is touching lives. So a lot of possibilities are there, a lot of business opportunities are there. And future manned mission you have mentioned. Definitely it is a step for manned mission to moon. But before coming to the manned mission to moon, there are steps wherein you have to do a sample return mission from the moon. Okay, you are not sending man or woman or humankind. You are bringing back some samples. Then it will go to moon. That is a different story altogether. For that only these human space missions are happening. We are getting capable in that domain also. So, in a nutshell, I think I have summarized what kind of opportunities, the doors of opportunities, this particular feat has opened up. And my objective of telling this is to inspire you to think in those lines. It is not only physics. It is also technology. It is also national pride, capability building. It is also a case of business opportunity. You have to think in all these angles. So that is my lesson, and I would urge you to carry this message to your friend circle. You should tell Chandrayaan 3 has not only achieved this, not only science, technology, but these aspects are also there. I would like you to spread this message among your friend circle.
Will do, sir. Will do. We have one final question.
Okay.
Send in the chat box.
Okay. What advice would you give to aspiring youngsters who aim to follow in your footsteps? First advice is don't follow anybody's footstep. Okay, there's the first advice. Second advice is don't think yourself as an expert. Okay, the moment you start thinking you're a top scientist, the concept of top scientist is a myth, I tell you, does not exist. If you are a top scientist, you are a big philosopher, and if you're a big philosopher, you will stop talking. Okay, so first of all, that ego has to be curbed. And another suggestion is one has to do a system thinker. System thinker means, first of all, interdisciplinary knowledge. Okay, when you are thinking about something, some subsystem, you are thinking about the whole system. You are proposing a solution for a problem. That problem could solve something in the electrical domain, but that should not cause something in the mechanical domain. Or you are solving something in the mechanical domain that should not cause a problem in the thermal domain. So you may work in a system, but you should have a system level view. Okay, that is very much necessary, not in terms of a space scientist or space technologist, in life also. So 3 things to summarize: don't follow anybody's footstep. Number 2, curb your ego, that is carrying no sense, which is unscientific. Third thing is be a system thinker. These 3 are the suggestions from my side, whatever I have learned so far.
That sounds good, sir. All right. Sir, thank you so much for your time.
Thank you
For sharing your
knowledge
and wisdom with us. Truly grateful, and we wish you all the very best for your future endeavors and
thank you so much.
things that you will accomplish in the future.
Thank you. You wish us the best so that the Aditya insertion is successful.
Sure, sir.
And the future missions are coming. Let us have success there also. Okay. And you also stay well, do good, and enjoy. Thank you so much.
Yeah.
Bye-bye.
Bye, sir. And that was Dr. Tirtha Pratim Das, everybody. Thank you all for joining this insightful guest lecture with one of the revered minds of our time.